Welcome back to the channel. This is the Earth Science Classroom. This video is on orographic lifting and how I explain, draw, and describe this type of lifting air over a mountain range and all different meteorology terms and processes that are included in this type of air lifting. This is the Earth Science Classroom. I love to do different techniques when I teach, and one of these techniques is to draw a very large diagram, an interactive diagram where I am talking to the students, I am drawing, I am demonstrating, I am showing how these processes combine into a logical and sequential diagram. And at the end of the day, like you see here, this is my finished diagram for the meteorology unit looking at orographic lifting, so how air is lifted over a very large mountain range. For example, this one is 3,500 meters high, or 3.5 kilometers, around 11,500 feet. And what happens to the prevailing wind that comes off a certain direction and makes contact with this mountain range and is forced to rise. So with these diagrams and with these basic processes, we can include a great deal of information, a great deal of different processes and parts of meteorology in terms of adiabatic cooling and heating, in terms of air masses, prevailing wind, the windward side, the leeward side, rain shadows, biomes. And as you see here, I start off with the left-hand side with the maritime air mass coming off the ocean full of water vapor, and it experiences lifting because of the mountain range that's blocking its path and forcing it over. So this prevailing wind is coming off the ocean, and I show that it's sea level, so 0 meters. At that elevation, it is 25 degrees Celsius. Now we can discuss the difference between adiabatic cooling and adiabatic heating with the change of pressure, change of temperature. We can also include the different lapse rates. So the ELR, the normal lapse rate, the DALR in terms of dry or unsaturated air, less than 100% relative humidity, or looking at SALR, which is a saturated adiabatic lapse rate, and how these two air masses and air characteristics change when they're going over this large mountain range. So the DALR is 10 degrees per kilometer for the lapse rate, so it goes down or up by 10 degrees per kilometer, or 1,000 meters. So in this case, it starts at 25 degrees Celsius. The air is going to force up, which means it's going to rise and cool down adiabatically at 10 degrees per kilometer. So at 1 kilometer it is now 15 degrees Celsius. The next kilometer, 2 kilometers in elevation, it is at 5 degrees. And I put there the dew point and the LCL, denoting where you have a phase change from water vapor to liquid water, condensation, and the release of latent heat. And you can go through what latent heat is versus sensible heat and how this is transferred within the air molecules and then released during condensation, which will build the cloud and change that air from DALR into SALR and change the lapse rate from 10 to between 5 and 6 degrees per kilometer, which slows down the cooling, which allows the air to build and form the cloud right there around the dew point and LCL. Then the air would continue with less humidity and the water being taken out into condensation, and the air would continue over the summit, and it will become minus 5 degrees because, again, it's DALR, and half of 10 is 5, so it goes up by 500 meters. So at the summit, the peak is negative 5 degrees Celsius, and then we start the journey down the leeward side, whereby you'd have the DALR being forced down because it's colder, it's denser, it's going to basically descend down the other side of the mountain range, and it will experience adiabatic heating, which is at 10 degrees per kilometer. So it goes from 5, the next point is 3 kilometers, as half a kilometer down, so 0 degrees or 32 degrees Fahrenheit, and then go down to the bottom of the mountain on the other side, which is at 0 kilometers, which would be at 30 degrees Celsius. So it's the air temperature, the ambient air, is warmer on the leeward side at the same elevation compared to that of the windward side. And you can discuss how the biome and the rain shadow and the lack of clouds, because air that is warming up and descending will not form clouds, and also a lack of water vapor, which is unsaturated and below 100%, even close to 30%. But this sinking air does not create clouds, so clear skies and higher pressure areas descending and warming, so you'd have different biomes compared to that of the windward side, which would have a lot more precip and high temperature, so perhaps a rainforest or tropical or temperate rainforest on that side versus a arid, semi-arid, or even desert conditions on the leeward side. So you can add in a ton of information on this simple diagram showing how the air is going to be forced over the mountain from one side to the other side, and the changes in atmospheric conditions, atmospheric stability, condensation, phase changes, and lapse rates and biomes, and even link this to locations like the Atacama Desert or the northwest of America over the Cascades. Or you could look at various other locations like the Himalayas and the Tibetan Plateau and the Gobi Desert. So all of these things are relative to real-world application and real-world geography and climates and landscapes and biomes, and definitely geomorphology. This is the Earth Science Classroom. Thanks for watching the video. If you liked it, please subscribe, like, and share. And if you want more content and videos on Earth Science, please check out my channel.